All right, so any questions?
Towers of Hanoi.
Yeah, I decided not to do it. I posted your next homework, and it's one induction question, and then it's some questions on counting, which we're going to start later today and work on Thursday and Friday. So those questions may not make sense yet. But anyways, homework 5, it's due a week from today. All right, Towers of Hanoi. So we've been talking about recursion and recursive proofs, and Towers of Hanoi is a good example of how we can use recursion to actually solve problems. So here's the setup, and there's some folklore that goes with this about Buddhist monks in a cave and the end of the universe. But they had 64 discs, and we've only got 6 discs here because I only have one pizza box to cut up. But here's the deal. Imagine there's 3 piles here that we can put discs into. Okay, so there's one here, there's one in the middle, and there's one on the end. And the goal is to move this pile of discs from here to here. And you have rules about how you can move. You can only move one disc at a time, and you can only put a smaller disc on top of a bigger disc. So for example, if I only had 2 discs, well, I can do it with 6. If I have 6 discs, the only disc I can move initially is this one, because you can only take from the top of the pile also. And I could put it here, or I could put it here. I could then move this disc either to here, or I can move this disc. And I can't put it on top of the smaller disc, so I'd have to put it over here. And now, there's nowhere I could put this disc, because it's got to go on a bigger disc. But I could move this small disc here, I could move it here, or I could move this bigger disc back here. So the goal is to find a series of moves that eventually result in this looking like this. And the question is, how do we do this in general? So if we try this with 2 discs, and we want to move from here to here, it almost does it for us, right? We only have one choice, which is to move this top disc originally, so we could move it there or there. And there's no point in moving this over here, there's no point in moving it back, so we're going to move this disc over here. And now the only thing we can do is move this little disc here. Well, we moved the pile from here over to here. That was almost what we wanted. So we can do that again, but instead of moving this little disc to the middle, I'm going to move it over here. I'm going to move this here, and we're done. So for 2 discs, not too bad. And the number of moves it took,
3.
Two discs took 1, 2, 3 moves. If I only have 1 disc, how many moves does it take to move from here to here?
1.
Bang, I'm done. So if I have 3 discs, it's not quite clear how to proceed. But does somebody want to try it? Do you know how to do it, first of all?
No.
Okay.
No, but I saw a good method for the first few discs. Probably work for that 6, but I'll start moving this one over here. Move this one over here. Here. And then I was like, right now, all of a sudden figuring it out. What's that there? There.
Cool. Thank you. You can only move 1 disc at a time. All right, so that was 7 moves. And we're starting to see a pattern. This is 1 less than 2, this is 1 less than 4, this is 1 less than 8. So for n disks, we might hypothesize it's going to take 2 to the n minus 1 moves. And we can prove that that's true. And when we prove it, we're also going to figure out how to solve this puzzle in general. So if you have 6 disks...
Yeah, just crank up the difficulty on us, why don't you?
Yeah, you want to do 6?
If you want me to try, I will.
So if this is true, it's going to take 63 moves, assuming you don't make any missed moves. And if you make a mistake somewhere, it's going to take more.
I think after about 12 or so, you should see the pattern.
Yeah, so there is a pattern.
Yeah.
Suppose that I knew how to solve this problem for 5. So let's make this look like 215. Let P of n be the proposition. You can move n disks. We know that P of 1 is true because it's easy to move a pile of 1 disks from one peg to another. It takes 1 move. So what we'd like to know is, can we show that P of n gives us P of n plus 1? If we can show that and we know P of 1, we can prove P of n is true for any n, and that there's always a solution. So suppose I know how to solve this puzzle for n disks. Can I solve it for n plus 1 disks?
I mean, I know for sure if you know how to solve it for n, you can solve it for n minus 1.
True.
I know that for certain because solving 3, you used a chunk of solving 2 right at the start there.
Okay, you're really close to the key intuition here. Suppose I know how to do this. Bang, boom, 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 bang.
That's 5.
That's 5. So suppose I know how to solve P of 5. Start with 5 disks here, do my thing, end up with 5 disks here. All right, now, Mr. Smart Guy, here's 6 disks. Let's see you solve that. Boom, 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 do my thing. Bang, boom, 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 do my thing.
Yeah.
If you know how to solve it for 5, it's trivial to solve it for 6. Use your 5 moves to go from here to here. Use 1 move to go from here to here, and then use your solution for 5 disks to go from there to there. And we can use that to figure out how many moves it takes to solve it for n. Because let's make a new proposition. Q of n says n disks takes 2 to the n minus 1 moves. Q of 1 is true, because 1 disk takes 2 to the first minus 1, that's 2 minus 1 is 1 moves, we know that's true. So assume Q of n So how many moves does it take for n plus 1? However many moves it takes to move n disks, so it's Q of n, plus 1 move to move that bottom disk, plus the same number of moves it takes to move n disks.
Although that looks more like over and to the n plus 1, no?
Does this formula make sense though?
I see how you got it. I'm not.
Make sense
I'm
to
not
you?
sure how it
This is the number of moves to move the top n minus 1 disk, right? To move 5 disks from here to our 3rd peg. That's going to take Qn moves. It's going to take 1 move to move this to my middle peg. And then it's going to take another Qn to move these n disks from here to the middle peg. Well, what is Qn? Qn is 2 to the n minus 1. So this is 2 to the n minus 1 plus 1 plus 2 to the n minus 1. Sorry, I need an eraser. Right, since Qn is true, it takes 2 to the n minus 1 moves. And Qn is 2 to the n minus 1. So that's 2 times 2 to the n. Minus 1 plus 1 is 0, minus 1 is minus 1. And 2 times 2 to the n is 2 to the n plus 1. So Qn plus 1 takes 2 to the n plus 1 minus 1 moves.
I think I can see the pattern, but if we don't have the pattern, how can we make sure that the one before the last step is going to be the bigger one on the left side and the rest of it on the right side?
Well, we're starting with this setup, right? And so we know the biggest one's got to be on bottom because you can only have disks on top of bigger disks.
Right.
So the one on the bottom's got to be the biggest of all. So I ignore that for a moment and I say just move these 5 disks.
Okay.
And we know how to do that because we said we know how to solve it for 5.
Right.
So instead of moving them here, I just move them here. And now there's nothing in the middle, so I can move this over here. And now whatever I do to move these is going to be legal because all of these are smaller than this. So I do whatever I did to move 5 disks to a peg, and it happens to have my big disk underneath. But how do I solve it for 5 disks?
Do 4 disks and then move your bottom.
If I know how to solve it for 4, it's easy. Move my 4, move this, move my 4. But how do I solve it for 4? I don't know, but if I can figure out how to solve it for 3, I'll move my 3, move the middle, move the 3 back. Do I know how to solve it for 3? Yeah, I can just ask someone who knows. Or if I don't, I can say solve it for 2, move this, right, which was actually the solution that he came up with. So to move 2, we move 1, put the big one in the middle, move 1 back. That's your base case.
But that's not even the base case really, because the 1 is the Qn plus 1 plus Qn.
Yeah.
Yeah, so that's like,
Yeah.
Isn't it slightly different for like the more disks you have because like in that case you start off with 2 free spots, but if you're gonna do 6, you only, I mean, 1 spot is always taken up by that.
It's not though.
since it's bigger, you can use it.
Since it's bigger, right? So I can move these over here, and if I need to move any of them back to here at some point, I can always do that because this is the biggest. And you can show that inductively also. Yeah. So that's a classic problem, and the storyline is there's these monks in the cave doing this with 64 disks, and they're basically counting down to the end of the universe, and when they finish moving all 64 disks to another peg, that's the end of the universe, and everything disappears. And it's going to take them 2 to the 64th minus 1 moves, assuming they don't make any mistakes. And so 2 to the 30th is a billion. 2 to the 60th is...
It's 1.84 times 10 to the 19th.
Yeah.
That's pretty big.
So 10 billion seconds if it's 1 second per move. So we got some time. And you can write a computer program to do this, and it's recursive. You say, if I only have 1 disk, just pick it from here and put it there. Otherwise, solve it for n-1 disks to go onto this peg, move the bottom disk here, solve it for n-1 disks to go from that peg to the middle.
Oh, I got that.
The solution or the coding of it?
No, it's the process of running the program.
Boom. So it depends how quick it is. So in 223 last year, I showed this in some Java code because we were playing around with graphical interfaces. So I did a graphical version of this, and you could watch it moving from one spot to another. And I think we did it for like 20 disks, and it never finished. So 2 to the 20th is 1,000,000. And I think I was doing 1 second per move. All right, so that's another example of recursion and using mathematical induction to prove propositions. And in this case, as with some others, the inductive proof actually gives us a solution, because we can code up P of 1, and we can code up the step from P of n to P of n plus 1. And that's a pretty efficient recursive solution.
It's crazy how fast it is to code.
Yeah.
Like, because somebody had posted on Canvas in the discussion forums asking if anyone had thought of any other functions, and I was saying that triangle numbers would be
Yeah, I saw your triangle and somebody else.
And it was like, oh yeah, I just coded it up. It was, wow,
Yeah.
it's really fast.
I
It
thought
really
CSE
is.
would be really hard, but it was just...
Dude, it's
lends
crazy
itself
how
to
fast it was. Because I just felt like, oh, it's probably just this. And then I was, well, I can try it because it takes like 2 seconds to code that. And then it's really fast to code it.
Yeah. So we can start to view more and more of the world as recursive functions.
Yeah, it seems like the mathematical ones are intuitively really easy to do.
Yeah.
Yeah. Like, it was harder to think of something that wasn't a mathematical formula.
Recursive directory listing.
Yeah. So more generally, a search problem. You want to search an array of numbers for some particular number. So search array number. And let's say your array is not sorted, right? So if array is empty, return false. Our number's not in the array. If number equals, so let's say array length number. So if length equals 0, then there's nothing in the array, we don't find our number. If our number is equal to array, and we'll forget about index origin 0, because it's just pseudocode. If the last element of our array is our number, return true. So if there's nothing in the array, we didn't find our number. If the last element of the array matches our number, we did find our number. Otherwise, return search array length minus 1. In other words, take the array without the last number included and see if your number is in that smaller array. And if it is, then return true. If it's not, return false.
I feel like it's really slow.
It's slow because we're doing a function call each time, yes. And it's using up resources to remember where we are. This is something called tail recursion because the recursive call is at the very end. And if you have a tail recursive function, it's pretty easy to change it into something non-recursive. But it's really easy to write, and I barely had to think. And I don't have to do any looping. And that can be kind of nice. And we'll find algorithms when we talk about object-oriented programming in 223. We'll work with algorithms that sort of have a natural solution that's recursive. For example, there's a problem called the Knapsack Problem. And it's pretty hard to write a solution to it that's not recursive. It's very easy to write a recursive one. The Knapsack Problem is saying if I have a bag and I want to put up to 20 pounds in it, and I have this inventory of items, they weigh different amounts, they're worth different amounts, which item should I put in there to get the maximum value? So it's like the shopping spree thing. right? You're allowed to take 20 pounds worth of stuff from Office Max. Which thing should you take to get the maximum value? And you can express the solution really, really easily recursively. You can say, well, if I put in this item which weighs 1 pound, what's the most value I can get from the remaining 19 pounds? Add that to the value of this. If I put this item in which weighs 3 pounds, what's the most value I can get from the remaining 17? Add that to the value of this item. Do that for each item, take the maximum value. That's your solution. And it's recursive because we need to solve the problem for smaller weights. Solve it for 19 pounds or 17 pounds and so on. And it's a huge search tree. But the code is a few lines. And that one doesn't have a sort of natural, just change it into a loop kind of thing like searches or factorials or triangles.
I did have one question.
Mm-hmm.
When I ran my triangle number 1, I could run it up to like 9,000 or 9,500, and then it would start to give me big negative numbers. So I'm guessing, is that like some memory issue where it was just kept falling?
No, that's probably just an integer overflow.
Okay.
Because 10,000 triangle will be around 10 billion.
Yeah.
So somewhere south of that, you'll start hitting this 2 billion limit on integers.
Okay.
And it just overflows.
Gotcha.
But if you did a much bigger number, yeah, you'd eventually run out of memory. Mm-hmm. And when you run low on memory, a few things can happen. Your program might just exit. You might get an error saying no memory. Your whole system might go south. It really depends on the environment you're in.
Yeah, I think when I ran it on 1 million, it just blew up and didn't give me anything.
Cool.
Yeah.
Yeah.
When I mentioned searching, I meant like on a Unix structure, for example, like you're going through the directories. So in this case, you'd have your search function, but it would be like a multi-dimensional array with arrays inside of it. And then every time, and you loop through it, for example, and if you come across an array, you call the initial sort of a search function on that one and go through it again, yeah?
Got it, yeah.
So like every time you find a directory, you call your search directory.
Yes.
Yeah.
Yeah, so file search actually is a really good example because we have this natural structure. Right, and what do we have to do? Just see if it's in this subtree, see if it's in this subtree, see if it's in this subtree, and we're done. How do we tell if it's in this subtree? Well, search this subtree, and we're done. Right, that codes recursively really nicely. And when we talk about trees, we'll use recursive definitions and algorithms to do things like visit every node within here or search for some particular value and so on and so forth. You got a question?
Another cool example like that is maze solving.
Yes. I'm horrible at drawing mazes freehand. But maybe I'm not so bad. Right, so you want to get from here to here. And you come down to the first point where you have a decision to make. Should I go this way or this way? Well, solve two subproblems. Suppose that this is my maze without this corridor, and I'm going in here. Can I find a solution? And then say, suppose that this is my maze and I'm going in here. Can I find a solution? And it's a few lines of code. Right? All the challenge is just setting up a maze and knowing how to move through it. But to actually find the solution, you're trying all the possibilities, basically. And this is what we do when we solve a maze, or what I do when I solve a maze by hand. I hold my finger here and I say, okay, I'm just going to try to solve the problem from this point forward. And if I don't find a solution, I'll say, okay, I'll try this way. And if I don't find a solution to either of those, then I'll say, okay, let me try it from this point forward. And you just keep working like that. So you can start to think of more and more things recursively. And mathematical functions fall out like this all the time. So 2 to the n equals 1 if n equals 0, 2 times 2 to the n minus 1 otherwise. That's kind of a weird way to define 2 to the n, but that lends itself to coding really quickly. But whenever we do this, we always need this base case. In some sense, that's the base case of the inductive reasoning process. If we don't have that, we sort of go down the rabbit hole forever and we never come back. When we try to compute 2 to the 20th like this, we go down, 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 we compute to the 19th, 18th, 17th, and we just keep deferring our actual calculation until we get to trying to compute 2 to the 0. And at that point, we don't have to recurse again, we use our base case. And once we have that, we start popping back up. And if we're lucky, we come all the way back up to our original version of our code and we come up with our value. So one of your homework questions that I posted asks you to use De Morgan's theorem and inductive reasoning to prove a generalized De Morgan's theorem. For example, we can show that this is true. First of all, this is De Morgan's theorem, right? We're given this. We can actually show that this is true using this pretty easily. It's a few steps of algebraic manipulation. And if we know this, we can actually show this with no extra work other than having to write some more symbols. But we can't really show this directly from here. I mean, we can, but it's a pain. But if we know this for 25 symbols, it's really easy to show it for 26. And when you find a problem like that, that's when you should start thinking induction, and then start thinking recursion. Induction is useful when we have in our minds an intuitive idea how to get from n to n plus 1. But we want to prove this for all n. And you can prove that this is true for any number of terms using induction and this. So that's what the first homework question is. So play around with that. Let me show you one other example of this, which is not on the homework. So matrix multiplication. Remember how this works? We multiply rows and columns, we take their dot product, and it gives us the 4 entries. So if we have right, so our upper left corner is the first row dotted with the first column. So 2 times 1 plus 2 times 1, that's a 4, and so on. All right, so here's a theorem from Matrices. And raising a matrix to the n just means multiply by itself n times. That if you have zeros here and here, you can raise this whole matrix to the n just by multiplying these 2 elements to the n. And it's generally not true. We can't just take an arbitrary matrix and raise each element to the n. But there's a theorem that if that upper right, lower left are both zeros, then this is a true statement.
Does this work for a 3x3?
I think so.
And you would just have to have zeros in the upper right and upper left, or zeros?
I think everything except the diagonal.
Okay.
So if you wanted to prove this, you might start with the case where you're squaring. And so So upper left will be first row, first column, that's a squared plus 0. Upper right will be a0 times 0b, that's 0 plus 0 is 0. Lower left, 0b dotted with a0, that's 0 plus 0. And lower right, 0b dotted with 0b, that's 0 plus b squared. Hey, it works for 2. And if you try it for a cubed case, it starts to look familiar. A squared times a plus 0 times 0 is cubed. This is still going to be a squared times 0 plus 0 times b. 0 times a, b squared, 0 is a 0, and then 0 times 0 plus b squared times b. And you do this and you realize you're doing the same thing every time. So how do you generalize it? And you could try to plug in an n here and show that you get that. But you can also do it with induction. So P of n is the proposition that this is true. And P of 1 is true, because if we just raise this to the first power, we just get the matrix back itself. And then if we assume P of n, then this thing raised to the n plus 1, we know is just this matrix raised to the n times the matrix one more time. That's matrix algebra and definition of raising to the n plus 1. And by P of n being true, we know that this is equal to this. And so a0, 0b to the n plus 1 is equal to this product. And that's a matrix multiplication we can easily do. A to the n times a is a to the n plus 1 plus 0. A to the n 0 plus 0b is 0. 0 times a, b to the n times 0 is 0. And 0, 0 plus b to the n times b is b to the n plus 1. And so we've proven this is equal to this if P of n is true. So P of n implies P of n plus 1, therefore by mathematical induction, P of n is true for all n bigger than or equal to 1. And we can do that because we could show this for n equals 3, 5, 100 by just continually adding one more to the value of n. But to show it for all values of n, that's where we invoke by mathematical induction. And it lets us generalize what seems to be true and what we feel is true because we've got a procedure for getting from n to n plus 1, and we know we just have to do that enough times. It's exactly what induction does for you. Good. All right.
We're going to learn to count now?
Let's learn to count.
Okay, who's this?
Yes.
Oh, God.
There's a Halloween costume.
Mathematically inducted count?
Yeah.
What proof did we do?
Counting. So, we're going to learn something called the product rule. And here's what it says. Suppose a certain procedure can be performed as a succession of two tasks. So we have some procedure we're trying to perform, and we can break it into two tasks, T1 and T2. First you do T1, then you do T2, your procedure is complete. So I'll call this procedure P. Okay, here's what the product rule tells us. If there are n1 ways to do T1 and n2 ways to do T2, then there are n1 times n2 ways to accomplish your procedure to do P. And this may seem simple, but we're going to do a lot with this. But we'll start with some straightforward examples.
What's the semicolon? What do we call it?
What?
1 times 2 times n2.
N1 times N2.
Oh, okay. I messed up the.
Okay, for example, two people go into a room and they're both trying to sit down, and there's 20 chairs in the room. And you're not allowed to sit in someone's lap. So 20 chairs, 2 people. The procedure we're here is to get these 2 people to sit down. And we can break that into a succession of tasks. T1, first person sits. T2, second person sits. So how many ways can we accomplish this first task? How many ways can one person sit down in a room with 20 chairs? There's 20 possibilities. So N1 equals 20. This task is complete. This person is sitting in a chair. The next person tries to find a seat. How many seats are left?
19.
How many ways can this person complete this task? 19. So N2 equals 19.
Isn't that kind of dependent on T1 though?
Well, that's why there's only 19.
That's why there's only 19.
So there's 380.
So you're sitting in that seat, so I walk in, I can sit at any of the remaining 19 seats.
So there's 19.
Yeah, but the remaining 19 seats change.
Yes, but all you need is to know how many possible ways. Once you've completed your task, I can complete my task. And depending on how you complete your task, I'll have a different set of choices, but the number of choices will always be 19. And that's all that N2 is.
Because the first person always sits first.
First person sitting first, yeah, I'm turning it into a succession of 2 tasks.
So if you had to do this for seating arrangements for like a room full of people where all the chairs would be used, you would just keep subtracting 1.
Yeah, the next person would have 18, the next person would have 17.
And your combinations would get successfully more complicated because it'd be like 20 times 19 times 18.
Yeah.
That sounds like factorial to me.
It does. So N1 times N2 is 380. We can conclude from the product rule the number of ways that 2 people can sit in this room is 380.
It may or may not help to visualize this or slightly change the problem as 2 thieves walking into a room and stealing a chair.
That might help, because then the
Now
first
the
chair
chair's
is
gone.
Yeah,
The other guy can't steal that chair. It's just not there.
right.
So
But what if these are really big chairs? They're like sofas, and you can have 2 people sitting in the same seat.
we just count it as 2 distinct places to sit instead of seats.
Well, I'm going to say there's 20 sofas,
Okay.
and 2 people are sitting down, and they could sit on the same sofa, or they could sit on separate ones.
Okay.
So how many ways can the first task be done?
40. There's, assuming they can all sit 2 people to a sofa.
So there's 20 sofas to choose from. They can choose sofa 1, 2, 3, 4, all the way up to 20. There's 20 ways that first person can sit. I don't care which side of the sofa they're on.
So it would still be 20, and for the second person, it would be 20, but if we had a third person, it's 19.
Yeah, so the second person would still have 20.
It could be 19 in a certain situation. In another situation, the third person might be able to sit in 20 choices.
Right.
Where the first
Yeah.
person walked in, sat on the first sofa, and then the next one sat on a distinct sofa. The third person could sit on any sofa
True.
still.
So it's simpler with just 2 people. So, or if you can sit on laps, right? So the first person has 20 choices, the second person has 20 choices. In that case, there'd be 400 ways to accomplish this. But by saying that each person has a separate seat, or a thief is stealing chairs, then we only have 380 cases. All right, so student ID. You're attending Hackney University, and you got your student ID, which is tied to your financial aid. And your student ID is 1 letter followed by 1 digit. Hackney is a really small university.
And also a very insecure one.
Yes. How many possible student IDs are there? So our procedure is to assign a student ID to somebody, and we can break it into 2 tasks. Assign the first character and assign the second character. How many ways can we complete the first task of assigning a letter? 26. How many ways can we complete the second task of assigning the second character, which is a digit? 10. So there's a total of 260 ways we can assign a student ID. That's the number of student IDs available. Suppose your procedure is create a string of 8 bits. Each bit's a 1 or a 0. And the procedure is to create a string of 8 ones or zeros. How many different ways can we do that? We know that we can take a power of 2, but if we don't know that, we can use the product rule. We can break this into a series of 8 tasks. T1, pick the first bit. T2, pick the second bit. And so on up to T8, pick the 8th bit. So how many ways can we pick the first bit? How many ways can we pick the second bit? Right, because there's no constraint on what the second bit can be based on the first bit. How many ways can we pick the 8th bit? So the total number of ways that we can pick an 8-bit string is n1 times n2 times n8, which is 2 times 2. Multiplied by itself 8 times, that's 2 to the 8th.
Is it useful for like probability?
Yes, that's part of this unit. So how many truth tables are there of functions with 4 inputs? Throw some 250 at you. How many possible F's can we write using the product rule? task is to come up with a value for f for each spot in this truth table.
Well, we would break it up into each of the components, A, B, C, D. How many A's do we have? How many B's do we have? If we're using the product rule.
Okay. How many A's we can have? What do you mean by that?
Well, how many different combinations of A are there? If we're doing the truth table, it'd just be 1 and 0.
Well, we know we've got 16 combinations. That's 2 to the 4th. But how do we enumerate
2 to the 16.
f? Right, again, we have 16 tasks. This can be a 1 or a 0. This can be a 1 or a 0, and so on. 2 ways to do this, 2 ways to do this, 2 ways to do this.
Just
Multiply them out, 2 to the 16th.
looks you have 5 columns. 2 plus 5.
And if you have 5 variables, you have 32 tasks to complete. So it's 2 to the 5th. So for n input variables, you generally have 2 to the n tables possible. And you can show that with the product rule. And to show this in general, that n variables, 2 to the n, how could we do that for any n? Part of the answer is the product rule. Induction. I can do this for 4, I can do it for 5, I can do it for 6. How do I show that it's true for n? Mathematical induction. Assume it's true for n, show it's true for n plus 1. That's what I'm doing when I go from 4 to 5 to 6, and then say by mathematical induction, it's true for all n. Perfect.
What if the orders matter, like order of the rows?
Yeah, what if the orders matter? I mean, they do matter, right? We're picking the value here, and then we're picking the value here.
I mean, if we change that, it's another case. How many cases do we have?
Same thing. If I write it like this, I've still got 2 to the 16th possibilities. Right?
I'm talking about the whole table.
But the order that the table is in doesn't change what the contents of the table are.
Yeah.
Like the order of the table isn't a new case because it doesn't matter what the previous set of inputs on your ABCD were, because what you're not talking about like how many different ways can this table be written. You're talking about how many solutions you could have.
Yeah. All right, so we're out of time. We'll play with this some more tomorrow. We'll see some non-intuitive examples, and then we'll talk about the sum rule, which is for doing tasks that can be broken into either this procedure or this procedure. And we'll talk about the subtraction rule, and then we'll finally get to the pigeonhole principle, which is good stuff.
So it's been talked up in as much as Tower Hanoi has.